Good.
Okay. Perfect. I think it's also time now. If you allow me to introduce the speaker for today, I welcome you for today's a quantum seminar. It is the last seminar in this winter semester, and probably the last one that I'm organizing together with Anna, since I am now going to have other duties next semester. Our speaker for today is Professor Ronald Fernando Garcia Ruiz. He's an assistant professor at the Department of Physics at MIT. He studied physics at the Universidad Nacional de Colombia, from where he graduated in 2009. He obtained his master's degree in physics in 2011 from the Universidad Nacional Autónoma de Mexico. He moved then to Q Leuven in Belgium, from where he got his PhD in degree in 2015. Ronald became a research associate at the University of Manchester from 2016 to 2017. And then the year after, in 2018, he was awarded a CERN Research Fellowship to lead a local group for collinear resonance ionization spectroscopy. At CERN, he has led several experimental programs motivated by modern developments in nuclear science, atomic physics, and quantum chemistry. His experimental work provides unique information about the fundamental forces of nature, the properties of nuclear matter at the limits of existence, and the search for new physics beyond the standard model of particle physics. He's going today to talk to us about radioactive molecules for nuclear science. Ronald, the floor is yours, please.
Thank you very much, Mustafa, for the kind introduction. So let me be sure that it's working. So you see the screen?
Yes.
Okay,
yeah,
super. So yeah, thank you for the opportunity. So then I'm very happy to show you some of this work that we are doing in study radioactive molecules. So the key word here is radioactive, is that the nuclei of these molecules is radioactive. And what is important is that we can create this nuclei artificially in the lab with very extreme numbers of neutrons and protons. And this is interesting because by replacing a few nucleons, a few neutrons or protons, you can access to very different nuclear phenomena. This is by itself very important for nuclear physics because we can study how nuclear phenomena emerge. And one of our main questions is how we are going to connect this with QCD, right? With the theory of the strong force. But also, when we go to heavy collective nuclei, we can have very neutron-rich systems. So like here an example, calcium-52, 54. And these nuclei are teaching us about nuclear matter, right? We would like to connect our description of nuclei with things like neutron stars, for example. And these nuclei are our quantum simulators of these stars. And we can access to very collective nuclei with an asymmetric number of neutrons and protons, like this optical deformation that can be very useful to test the fundamental symmetries of nature. So overall, it's highly complementary. So we build this nuclei in the lab, and then we study a particular nuclear phenomenon. So before I go into the details, I would like to thank to many people, especially our group at MIT, that the students and postdocs that have been working very hard to show for some of the results they're going to show. And I will be mainly speaking about some of the latest results of the last 2 years. So that will be the main topic of this work. And this is part of a collaboration with 2 groups at CERN, COLLAPSE and CRIS experiments at CERN, with the support of many theories in nuclear theory, atomic theory, but for the work that I'm going to show today, mainly quantum chemistry, so with Robert Berger and Timur. So let me start with the motivation. So I was told to present an extensive motivation, and mainly for students, So the experts, it might be a bit boring for the experts, so I apologize in advance. But let me start by explaining why it's interesting to study molecules and why radioactive molecules in particular. So as I said, my main job is nuclear science. So we apply these AMO techniques to study nuclei. And traditionally, we have been studying nuclear science by colliding particles, right? We like to put particles closer together, then we like to go to higher and higher energies. So when we think about nuclear physics, naturally, we might think about these higher energy collisions. What we are doing is quite different, right? It's what we call the precision frontier. So we use the fact that the electrons in atoms or molecules has a probability to overlap with the nucleus. So higher the precision, higher the energy scale that I can prove. So I'd like to show that with this video, right? If you come to particle physics and you want to study a watermelon, so he will tell you collide with a high energy, destroy this watermelon, collect everything, all the reaction products, and then you can make a good reconstruction of what's inside this watermelon, right? You can make models that make a good description of how the watermelon pieces are connected. So what we do is quite different, right? We put an electron around this watermelon and we study it very precisely because we know that for some electrons, there will be an overlap with the inside of the watermelon. And higher the precision, as I said, higher the resolution of nature. At some precision, I will be sensitive to the properties of nuclei, how all these nucleons get together. And if I continue increasing the precision, I can be even sensitive to the structure of fundamental particles, like the electron EDM or sheet moment or nuclear EDMs that I will be describing later. So in a cartoon, this is, as I see, these experiments, right, in atoms, we access to different orbits that tell us different information about the nucleus, right? So the s orbits, for example, the electronic s orbits have some overlap with the nucleus. Then we use those mainly to access the nuclear radius. But because the symmetries of these orbits, we are not sensitive to some degree to higher order moments. So if we want to learn about the structure of nuclei, like magnetic moments or quadrupole moments, then we need to go to P3D orbits and beyond, right? With the price that we lost some overlap with the center of the nucleus. In general, we are mainly sensitive to the long range electron-nucleon interaction in atoms, right? You can be also sensitive with higher precision to our properties, but in general, I mean, the kind of experiments that we are doing. So the advantage that I see as a nuclear physicist, so in this cartoon, is that we can start with an atom like in an s orbit, put another atom next to it and create this kind of sigma orbits that is like a combination of an S and P, right? Still, I break the symmetry. So now I have an orbit that is something like the 4 orbit now that they still have access or with a good overlap with the center of the nucleus. So I can be more sensitive to the short range electron-nuclear interaction, right? So the real advantage is that the orbit looks like a combination of S and P orbits, so I can find states of different parity that are very close together. And we will see this will be a highly sensitive system to study parity violation. So in general, I can be sensitive to the short range electron-nucleon interaction. I can design these orbits of these molecules in a way that I can access to this part of the electron-nucleon interaction that is poorly known in most of nuclei, right? The nuclear electroweak structure, properties like a nuclear spin dependent, parity violation, right, through C exchange, or CW exchange inside the nucleus can create currents, and the electron can enter inside the nucleus and interact with the fields, the magnetic field, for example, produced with these currents. So these kind of properties we call anapole moments, and the group on Mainz is expert in this field, right? So you have a very nice experiments like Dima group going studying terbium. And the hope is that if I know very well the electromagnetic and the weak force, then I can use that to constrain possible new forces. So why radioactive molecules? Let's try to quantify this a bit better. So if I go to write down the Hamiltonian of the molecule, right, we have different degrees of freedom, electronic, vibrational, rotational, and so on. And at some point, I will be sensitive to the hyperfine structure that relates to the electron interacting with the nuclear properties. And if I go to higher precision, to parity by violating properties, and beyond to time reversal violating properties. And those are highly complementary in nuclear science. And that's because it's exciting for me to study those molecules, because with the hyperfine interaction, I can be sensitive, or I can test my knowledge of the strong force, right? I can access to these nuclear properties, and we can compare with nuclear models and in general. So what I'm testing here, my main goal is the strong force. Now, with the parity violating properties, I can be sensitive to a complementary aspect of nuclear structure, right? To the electroweak structure of nuclei. And it's a sector that is poorly known, and as I said, in many nuclei, so we can measure these properties that are so far unknown. And it's interesting because we have been seeing many experiments that are trying to use the weak interaction to prove new physics. And if I continue with precision, so I can access to parameters of the standard models that are predicted to be very small, like time reversal violating properties. It's basically a background free way to look for physics beyond the standard model. I can measure something that is non-zero, that the standard model predicts to be almost zero. So you see, it's highly complementary that I can test these aspects. So we have been using the hyperfine structure in atoms for many years, a low work being developed in Mainz, right, by the group of Professor Brian Neugaard and company, in which we have been using the hyperfine structure to prove or to study these exotic nuclei or these radioactive nuclei in atoms, right? And we can access, as I said, to these PT even properties, radius, nuclear spin, magnetic moments, and quadrupole moment. This is on highlight from our group and collaborators. It has been a very useful and will continue to be a very useful technique to access to nuclear phenomena. So in this presentation, I will focus in the force that we are doing in trying to go beyond the hyperfine structure, right? And as I said, this is interesting because the next term will be sensitive to the electroweak nuclear structure, and the last one will be sensitive to time reversal violating properties. And you have seen a few presentations in the past in this seminar that motivate this work. I will just go quickly, right? So we know that one of the conditions to explain the matter-antimatter asymmetry of the universe is CP violation that is equivalent, or we need CP violation beyond our current observations. And CP violation is equivalent to T violation. So in other words, by measuring these properties, we can look for this additional T violation that is still missing to explain the matter-antimatter asymmetry of the universe. But in general, right, so I can prove or test different extensions of the standard model. So experimentally, what it means is that I'm trying to measure these terms that are very small, but they appear as a product between a nuclear parameter and a molecular parameter. So I all the time trying to find the right nucleus that maximize this phenomena, the right molecules that maximize this factor. And of course, I have to do a good experiment to have the resolution to split this line and to look for this phenomenon. What is exciting is that it combines really nuclear, atomic, and molecular physics, both experimentally and theory, right? Theory is a strong motivator of this work, but also is guiding us, especially in the work with molecules. So the violating properties are not only coming from a product of nuclear parameters, they even for nuclear spin zero, then you can have T-violating properties in this Hamiltonian, but in this case will be coming mainly from the electron EDM interacting with effective electric field inside the molecule. In fact, molecules are becoming very popular, or have been very popular because of this, right? And you have seen some of this work in this seminar. So one example is the work of the acne collaboration using the thorium oxide molecule, a molecule that it can be polarized with a weak electric field, a few volts per centimeter, and the internal effective field that the electron experience can be of the order of 80 gigavolts per centimeter, right? Something far larger to anything that you can get in the lab, typically hundreds, perhaps of GeV per centimeter. And you can use that to test with the constrained electron EDM. So this electric field is overall about 2 orders of magnitude or more larger than in atoms. Why is interesting to constrain the electron EDM? So this figure is a good summary of that, of the work that has been done. So the different lines here represent the constraints to the electron EDM from different experiments. You can see that about 10 years ago, molecules took over this field and they have been improving continuously the constraints of the EDM, and different lines here or different bars show different extension of the standard model. So as I said, the standard model predicts a very, very small EDM, but there are extensions like supersymmetric models that predict some values of EDM. So further constraining this value means ruling out the existence or the validity of these models. Okay, this is just one example with some particular assumptions. So in this business, overall, we are looking then, as I said, at larger effects that comes from the nucleus of the molecules. And of course, it depends on the experiment, that is the interaction time and the number of molecules that I can have. Now, when the nuclear spin is different than 0, these nuclear parameters appear and they depend on the number of protons to some power, the nuclear mass to some power, and the beta 2 and beta 3 that are the nuclear quadruple and octuple deformation. And also in the denominator, the energy stays of different parity at the nuclear level, okay? And what is exciting in this radioactive nuclei is that you can maximize all of these parameters at once. You can access very large deformation, and you can access very large proton and mass numbers, and you can minimize this denominator. So overall, you can create nuclei like this radium-225 that have a factor that is about 10 to the 3 times larger than what you will find in a stable molecule, right? And there are even some nuclei like protactinium that are predicted to be even 10 to the 4 or 10 to the 5 times larger. I write in radium because it's one in which there is solid experimental evidence from no long ago. So then the motivation is great. So then let's try to put one of these nuclei inside of a molecule, and then we can take advantage or a combined advantage of this nuclear and molecular amplification because they multiply together, right? You can take the very best of all worlds. So that on paper sounds very appealing. Of course, there are challenges, and it's that it's very hard to produce these molecules, and that's part of the work that we are doing. So to give you an idea of the kind of sensitivity that we expect with these molecules, let me quantify this. So the figure of merit for parity violation scales with these parameters, the number of molecules, the interaction times, and you will see that the factor expected for parity violation for radium is about 50 hertz, which is gigantic for EDM experiments, right? That even with 1 molecule per second, in 1 hour of measurement time, with a coherence time of about 1 millisecond, you will be able to get these parameters with an uncertainty of 10%. Okay, it's really, the sensitivity is that large that with a single molecule, with a decent experimental parameters, right? You can still get this with an uncertainty of about 10%. And now for time reversal violating properties, like EDMs, I'm plotting here the EDMs constraints for several atoms, and neutrons and protons, electron and muons. So as I said, the thorium oxide constrained the electron EDM really very low, doing an excellent job. So there's a lot of progress in this direction. The other one is the mercury, also constraining the nuclear EDM. And there has been experiments in radium. So there have been experiments with the atomic case that has constrained this to the 10 to the minus 23. Now you can put numbers to this, the kind of fields, electric field that we expect for radium fluoride is 50 gigavolts per centimeter, which on this incoherence time and only 1 molecule per second, you can see that you will be able to provide a very strong constraint, right? So that's the kind of sensitivity being even competitive to the current limits. But the idea is not to compete with that, right? They provide us highly complementary aspects of these experiments, right? Nuclei is sensitive to this nuclear EDM, right? The shift moment. So we are testing mainly the hadronic sector, while most of the experiments in molecules now are focusing in the electron EDM. And then we decided to go and try to study one of these molecules. Radium fluoride was kind of the ideal molecule because it has the radium nuclei that has all of this amplification. The molecule has these very large effective fields. And on the top of that, it was predicted to be very good for laser cooling, right? Have the proper properties for laser cooling. The downside is that not much is known, or basically nothing is known or was known about short-lived radioactive molecules. And what it means to be good for laser cooling, it means that although the molecule has a very complex structure, so many vibrationals and rotational levels, it effectively works as a two-level system. So if I excite from one vibrational state in one electronic state to another electronic state, it will in principle prefer to decay back to the same state, right? It has a very strong diagonal factor, Frank-Condon factor. So then we wanted to go and test the experiment. That was true, right? It's indeed very diagonal. The lifetime of the excited state, you would like to be very short to apply a strong force, right? Optical force. And then you would like to have this isolated system because you would like to excite and not decay to different electronic states. So we wanted to measure the low line structure and be sure that it is indeed an effectively a two-level system. Laser cooling in atoms is a very well-established field. In molecules, it's a field that still is growing, right? So the first evidence of laser cooling was in 2010, and still there have been many developments in this direction. So in a molecule like radium fluoride, nothing was known, right? In atoms, you kind of can predict very well the lines that you are going to explore. So in molecules, no, at that level, right? Typically, theoretical predictions are about have an uncertainty of 10%. So we need to start really from the very beginning, study the electronic structure, vibrational, and so on. And the idea that a few years ago is maybe at some point we'll be able to actually use the molecule to study nuclear phenomena.
Ronald, a quick stupid question probably.
Yeah, please. Yeah.
I understand that the electronic structure is probably kind of similarly complex as in atoms, but vibrations and rotations should be straightforward. No, is that wrong?
Yeah, you can do better predictions. Yeah, definitely. But yeah, the main thing was first to find the electronic ones, right? And the vibrational and rotational, even though you can get a few percent, you still need to do an experiment, right? To identify the laser cooling transitions and so on. That's your question, Dimo?
Yeah, well, why just I'm wondering, is there like strong violations of Born-Oppenheimer approximation in these molecules, or what's going on? Why is it, I mean, rotations and vibrations should be straightforward, no?
Yeah, definitely. But the hyperfine structure, that is the final state that we want, we don't know, right?
Okay, got it.
And to measure that, we need to get that first. Yeah. So good. So then we went to do the experiments, and then we said, okay, hopefully one day we go there. We have to to know it experimentally well, and then go to these parameters. So here is the, let's say, the 3-step description of the experiment. So we first produce the molecule or the nuclei, which is a nuclear reaction. Then we have, once we produce this nuclei, these molecules, so we have to select the molecules because this is a very dirty process, right? So these molecules are producing in small quantities in highly contaminated environments and in a very hot environment. It comes from a nuclear reaction. So we have to separate the molecule using, in our case, we use mainly electromagnetic fields, and then study the molecule. So when we apply a combination of traps and lasers. So the challenges are those 4, right? So short lifetimes in the case of these molecules are days, no seconds. And we need precision, right? And typically precision and high temperature don't go together. So here is in a few steps, right? First, we use, we did these experiments at CERN. So we use protons from the PSV, about 1.4 GeV protons that collide with an uranium target. And then you produce many radioactive nuclei, among those radium. And then we inject CS4, some chemistry happens, you produce many fluoride molecules, and then we use mass separation to select mainly radium fluoride plus. Now we send the molecule that hopefully is pure, but it's not always the case because it's a hot environment, then you can have surface ionization of many more molecules, right? But then we must separate and send into a trap. This is a common pole trap, right? I have different electrodes because I have the common 4-pole trap, but we also have an electric field, a DC, to trap the molecules. So we use this to bunch and pre-cool the molecules because it's at room temperature. So it's filled with a helium gas. And at this point, the molecule, we think it will have room temperature. So now we use that to bunch and send into another trap, for example, the MR12, the multi-reflection trap, and in this case, isol trap, that we use to measure the mass of the molecules. Now we can fine-tune all the parameters in this production to be sure that we are mainly producing radium fluoride, okay? Depending on the temperature, we can either break the molecule, produce mainly radium, or we can, at some point, we just tune to best produce radium fluoride plus. Okay, this is an empirical process. Dima, you want to ask?
Yes, I'm sorry. I'm full of stupid questions today, Ronald. I'm sorry.
No, please, please ask.
But here, is it obvious that you want to make a molecule and then trap the molecular ion? Or, for instance, you might think of some other things like co-trapping different ions and making a molecule right there in the trap. Can you comment on that?
Yeah, thank you, Dima. So it's not obvious. So we are still investigating what's the best path to produce the core molecule. Yeah. So co-trapping can be a good one, and in the groups like Santa Barbara are doing that, right? So I think that will be a good step to, and we are all the time, we are doing traps. So one of the developments is to trap and have a cryogenic trap that I will show later on when we trap the molecule and try to do the studies there. But for spectroscopy, that's very hard, right? When you want to do the first spectroscopy, it will be very hard because then you don't know even if you create the molecule. There are indirect probes, but if you want to study the spectroscopy, that is the mandatory initial step. We have seen that very hard. And the group in Santa Barbara, for example, has been trying to do that. Yeah. Because you trap a few molecules, then if there are no diagonal, you don't know, and then you have to scan many inverse centimeters, hundreds of thousands of inverse centimeters. And with fluorescent detection, it's just very hard. Yeah. But yeah, we'll come back to that. Yeah. Thank you, Dima, for the question. So this technique has been used. Then we have produced the maximum number of molecules. Then we are sure that we produce this. It's a very ad hoc way to do it, right? It's a lot of try and error because this chemistry is very complicated. But luckily, we have many experts that they know very well what they are doing and they are supporting this work. And then we tune everything to produce the maximum number of molecules. Just to give an idea, typically in these experiments, about 10 to the 5, 10 to the 6 molecules per second we are producing. Although we can push everything to the extremes and And in practice, we can produce more than 10 to the 9, 10 to the 10 molecules. So now, once we produce this bunch of molecular ions, we pass through a charge exchange cell. So this is a hot vapor of sodium. And the idea is that sodium gives an electron to radium fluoride to produce the neutral molecule in flight. So we select sodium because the theoretical predictions told us that the ionization potential of sodium and radium fluoride plus radium fluoride were similar. So we have a kind of resonance or quasi-resonant charge exchange cell process that hopefully will populate radium fluoride plus radium fluoride neutral, mainly in the ground state. And then once we produce the neutral molecule, that is the one that is interesting for this study, right? The ones that has the proper symmetries, then we can send different lasers to study the properties. Okay, one typical way to do that is either you excite and see the fluorescence, but this is a very inefficient process. So what we do is resonant ionization, right? We have at least 2 lasers, and at the end we can separate neutral and ions. So the idea is that we fix the second laser, right? This is all the time present and has enough energy that if the first laser excites the electron from the ground state to any excited state, then the second laser has enough energy to remove the electron, right? So in a typical experiment, you leave the first laser fixed and you scan, sorry, the second laser is fixed, the first laser is being scanned, and then we see the counts in this detector, right? After the deflection. In principle, if the first laser is not present, is not in resonance, then you only have neutral molecules. But when the first laser is on resonance, then the second laser has enough energy to ionize. So you see an enhancement in the counts on this detector, okay? Very simple in principle. And there are many more details to say here. So I will present a video that the PhD students organize and the undergrads to present all the details of the experiment. I think it's a very nice way. Let me be sure that I share in my zone. And just tell me if you hear.
We overlap
It's working.
the isotopes with lasers.
Play me with some bass and drums, cause I'm about to go crazy dumb. Pay me some attention and I'll educate your cranium. Crystals, yeah, we're lasing them, sapphire and titanium. But wait, I'm out of order, so let's start it at the target. We irradiate uranium, then some decays to radium. Inject fluorine, we're making some radium monofluoride molecules. They're pretty hot and they gotta be cool. Prior to use the spectroscopy tool, apply a strong field and they follow the rule. Cause they're energized with the ionized tool. Follow my drift if you had left school. If not, don't sweat it, don't matter, my dude. I can't break down kinematics for you. 40 kV make the cations move. Yeah, that's electrostatic extraction. Next we filter, then we trap them, flapping quadrupole attraction. In Paul trap, we buffer gas them, and that causes cool reactions. The ions are not static, scatter non-adiabatic, so the cooling's automatic. Yeah, it's quite a useful tactic. Helium gas collisions induce a few transitions, reducing our partition function, thus upping precision. Next we're onto the charge exchange. Gotta change my flow, make the bars insane, so the beat pass through a sodium vapor, RAF, an electron taker. Neutral molecules exit the chamber, deflect the rest like see y'all later. Now we're back to the PISAP laser, scanning wave number and logging the data. Ion state of annihilator, level structure interrogator, cause molecules are resonators, responding to strong oscillators. See figure 1 from our paper in Nature. Next we pulse with a 355 nanometer light, reionize only if we already excite. Ground state sigma to A2 pi, or a higher lying state if the scan laser resonates. Ions are detected once deflected to collection plate. Tweaking the frequency, seeking some evidence, seeing a peak when we sweep through a resonance. Technique is elegant, sleek and intelligent, speaking out beats, I'm a geek in my element.
We'll see a few examples in radioactive molecules having the ability to modify the neutrons and protons inside the molecules, allow us to explore very different phenomena.
Alright, we've covered methods. Let's focus on results and goals. First of all, we had to probe positions of the manifolds for vibration normal modes, plus Frank-Condon factors, so we know if we could trap and slow gamma damp molasses cold. I'm talking laser cooling, if that wasn't understandable. It's important for precision measurements on things like anipodes and other such moments that don't consider parity, plus deviation from king linearity, time reverse breaking, comparing polarities, find such a constant to track regularity. Unstable isotopes we produce scarcely, some of these signatures enhanced apparently from certain structural irregularities like deformations or large angularity. Got all that? Alright. Molecules, they magnify permanent dipole moments. Plus they have more transitions to measure isotope shifts and isolate components that are higher than the lowest order terms of standard model effects. Count for them all, then what do you get? Well, if you are left with signal excess, it could be a sign of 17x or other dark bosonic coupling strength. Axion field, your shot I will check. Shout out to Voltage, with whom we're doing this tangle state measurement technique is ludicrous, though we are new to this method as used in quantum computing with trapped ion qubits.
We call this kind of flow a super flow.
And the fruits of all our science could have practical appliance, like nuclear optical clocks, to keep time with. In a smorgasbord of tactics yielding ultra-narrow line widths, we keep climbing ever higher, standing on the backs of giants. At CERN never been triumph, looking for PT, we'll find it. Then our paper, we would write it, and then you should probably cite it. Oh my bad, I got excited. I'm just saying, future's bright and all the factors in alignment. That's a wrap, hope you liked it.
There was a nice one that explained the details of the experiment. I think that is the most fun way that I can do. So
not bad. That was actually
Yeah.
pretty impressive. Jesus.
Absolutely
quite nice.
hilarious.
Who is the artist? I mean, is he on YouTube? I want to follow him on Spotify.
But it will be here in this talk, so if they want to see a video, because unfortunately they didn't use masks. So I cannot put that in YouTube yet because the MIT policies of using masks in the lab. So, but good. So I hope that the point was clear that there are many steps of this experiment, and the challenge is that are many unknowns. Each step is unknown. We didn't know the molecules that are going to produce. Right, you're sending this fragile object with very high energy for TV to a trap, right? That is filled with helium. So we don't know how many we're going to break. And then you reaccelerate to high energy and collide with sodium. So we didn't know what was going to happen, right? Many of those were open questions. And theory can do a prediction of these electronic transitions with a few percent, like 10%, that's large, right? 2000 inverse centimeters, right? That's a very hard, very difficult region to scan, right? But luckily, so we were quite successful, right? We have many lasers and we do collinearly and anti-collinearly. So then effectively we are proving two different regions of the frequency space with each laser. Okay, and we send in this case at least 3 lasers. It's a very effective way to scan these transitions. So then we succeed, we measure the electronic structure. These, for example, here are transitions between different vibrational states of different electronic states. And you see this very beautiful spectrum, right? 0 to 0, 1 to 1, and so on. Indeed, mainly populating the 0 to 0, the lowest states of the molecule, which was a good surprise. And the space between these was, you can already say that it will be good for laser cooling, but nevertheless, we can measure everything. We measure well, everything that we can, right? So the non-diagonal terms were very weak. So indeed, it's quite diagonal. We measure the lifetime of this state, that is very short. Good news for laser cooling, and all the excited states that we found agree with the theory, and they were above the electronic level that in principle you can use for laser cooling. So overall, very good news for laser cooling. As a postdoc said, we are proving that these hot molecules can be super cool. And we were happy because although it's the first step, right? Electronic and vibrational that we are measuring now. So it got the attention of our communities. So after that, we have astronomers that came to us, for example, and asked if we can do some radioactive molecules for astrophysics, right? Or people from quantum, well, kind of related quantum chemistry and astrophysics. So it's on a small step. So still there is a lot of work to go to the final goal. So now that we can create the molecule, so we know how to create and study the molecule, then we can start playing the games that we like to play, adding neutrons into the nucleus and seeing what happens with the structure of the molecule. So this is one example of this work. Now we add neutrons into radium, and now we can see for effects even at this low precision. It was a good surprise for us that we were very sensitive to the isotope shifts, to the changes of the nuclear size of radium, right? So it might be obvious now, but that was not obvious at that point for us. So see, this precision is 0.1 inverse centimeters, right? And the distance here is mainly given by the change of the nuclear radius multiplied by the equivalent of the field shift in molecules. So that was great, because at this level, then we can already use that to learn something about the nucleus. Radium was known, but we can use that to benchmark our knowledge of the experiment and the quantum chemistry, which did, by the way, a very good job. And with many perspectives, then we can use one of the challenges of study actinide isotopes is that they like to form molecules, right? So at this solid, it's very hard. We have not been able to extract them as an ion or atom. So they are very reactive, they form molecules. We can use the molecules to study nuclear properties, then that's very good news. So we want to go beyond, and as I said, so going beyond, we need higher precision. And one of the advantages of doing this work collinearly is that we can access to high precision because we can reduce the Doppler broadening. So, right, you know very well that one of the challenges is the Doppler broadening. If I just plot the kinetic energy versus the velocity, you see that any small energy spread corresponds to a very large spread in the velocities, right? That's I think it's very well known for all of you, the Doppler broadening. So many people do laser cooling to reduce this energy spread, right? And we have very beautiful works like laser cooling in many labs. But the good news for us is that if you get energy, you can have even the same energy spread, but you get energy to the system at higher energies, the same energy spreads correspond to a very narrow velocity spread, right? So the line width, the Doppler width scales inversely with the kinetic energy of the ion, and you can put numbers that with just a few keV, like 40 keV, then the Doppler width will be of the order of megahertz. That's great. We have been using this technique for many years. In fact, it was developed mainly in Mainz, right? So there was a lot of developments in the early days of these techniques to study atoms with this collinear laser spectroscopy, taking this advantage. And we did that, right? And now we can access, this is some preliminary data, we can access the rotational structure of the molecules. And now once we know well the rotational structure, we can replace the nucleus by a nucleus with a spin different than zero and access to the hyperfine structure. So these are just some old data. A few months ago, we did a very beautiful experiments. Now we have a very nice rotational and hyperfine structure of these molecules. So that's going far beyond what we expected a few years ago. So we are approaching our final goals, but from here to here, we need a big step. So still going on, stay tuned, and hopefully that will be published soon. Now we have a very precise knowledge, a very good knowledge, experimental knowledge of the molecule, the laser cooling scheme. We study very well these transitions. So the work is in preparation. A lot more that we learn about different ionization schemes. So we now have a very good knowledge of this, the structure of this molecule. Okay, what are the current developments? We want to go beyond, right? And to study parity or time reversal violating effects. In general, we have to do, well, if you see the figure of merit, we have to increase the number of molecules that we could prepare in the state that we want to study. And we want to increase the interaction time, right? This technique that we use is very good to do spectroscopy, right? A very fast and efficient way. But once we accelerate, the price that we pay is that we lose interaction time, right? So then perhaps the final goal is not to accelerate, but actually to cool down and trap these molecules. So there are mainly two techniques to measure this. For parity violation, one of the techniques that is being used is to interact with an oscillating electric field, right? That's group like David Emil is doing, right? Very nice progress in this direction. Or to measure EDMs, you need to put the molecule to interact with a DC field, right? Then you polarize the molecule and then you measure the EDM. So the key message is we need to trap the molecule and either make it to interact with an oscillating electric field or a constant electric field. And the developments can be quite different in these two directions. The other good news is, as Dima was pointing out, so there is a lot of developments in traps. So this technology has been developed, like the group of Eric Cornell, for molecular ions. For neutral molecules, it's still quite challenging. We are still thinking how we are going to slow down and trap these neutral molecules. There are many ideas, but for molecular ions, we have a better knowledge. At least there is technology that has been developed by our groups, and I think you have a seminar about that not long ago. So I don't want to go through all the experimental details, but overall, we start with this very hot and fast molecule with a large energy spread. And we would like to end with a cold and trap molecule with very low energy spread, of course, the coldest that we can. And there are many steps to do that because we need to do that efficiently, right? These molecules are very expensive, very difficult to produce. If we produce one, we like to take it to the very end. I will not go through the details, but I will be happy to come back if you are interested. So the trapping technology, as I said, is known for EDMs. Something that perhaps is less well known is for parity violation. Well, I mean the technology that we are developing is that if you go for parity violation, so that has been used for many groups, and Dima group is working on this field, right? So one of the ideas is that if you want to look for parity violating properties, then if you don't include the weak interaction, states have very well-defined parity. Once you include the weak interaction, you have a mixing of states of different parity. And although the numerator is very small, the denominator depends on the energy difference between these states of different parity. In molecules, these are naturally very close, right? In atoms, you can find special cases, but normally in molecules are relatively like 10 to the minus 5 times smaller than in atoms, right? And this provides an advantage because you amplify this term by many orders of magnitude comparing to atoms. Most of the atoms, right, you can find special cases. So then they are already so close in energy that you can actually apply a magnetic field and bring these two states close to zero, right? Close to the same energy. And groups like David Emil have proved that this enhancement can be more than 10 to the 11 orders of magnitude. So this was quite exciting for us because this enhancement right at 10 to the 3, 10 to the 6 is great, but 10 to the 11 is really telling us that what we thought will be impossible can be very possible with molecules. So then we join efforts with David Emil, and the idea is that we're building a penny trap. And penny trap seems like a quite ideal device for this because we can tune the penny trap. If we go to calculate the magnetic field that we need to do this crossing of levels, is about a few Teslas, right? Or about 1 Tesla. And it's precisely the kind of magnetic fields that you use for penny traps. So the idea is then you put this molecule in the trap and then tune the magnetic field to interact with the molecules while you have this situation of maximum enhancement of this term, okay? So this work is being done. So we are working with David Emil and other groups in the United States with the strong support from our German collaborators that have a lot of experience in these penny traps. And if you want to know more about that, I will be happy to let you know about the current progress of this experiment. So this is conceptually the idea. So many future opportunities, just to end. So I like to think as an experimentalist in these two axes, right? Sensitivity and precision, right? So many of the developments that we have done has been in sensitivity, right? We didn't care much about the precision, so we are far away in the AMO evolution of techniques. And there was a very good reason, because with the precision that we have, was enough to access to the nuclear observables that were interesting for us. All of those are interesting, right? Symmetry violating properties, but we saw them so far away in precision that we said we consider that impossible for us. I mean, people working with radioactive ions, our groups and collaborators. But with molecules, you kind of send all of these observables to the left, right? You have a sensitivity, you have an amplification of the sensitivity, So we think that if we combine precision and sensitivity, then we can hopefully access to these observables. So it's giving us a strong motivation to work not only towards sensitivity, but also towards precision. And I add in sensitivity, there are very nice work like the Mustafa for super heavy elements or resonant ionization work in source and dissolving. So there are, in precision, there are many good works, laser cooling with that 10 to the minus 16 and 18 precision, right, for some specific atoms, but not as sensitivity as we need for this kind of experiments. Sensitivity meaning here that I produce one ion, or then I will be able to take this ion and study, right? That's what I mean with sensitivity. And we are scratching the surface of many opportunities. So that's kind of the example that I showed you. There are many possibilities for developments, not only of the technique, but facilities. There will be many of these facilities that will be able to produce these nuclei in very large quantities. And especially the EFRIB facility, the facility for rare isotope beams in the US. Because this facility is going to produce all of these actinide that are poorly known so far, with very large quantities. What is fun is that actually it will be the garbage of this facility in many cases, because they will do nuclear reaction with high energy, they select only one isotope and they throw away most of the isotopes. And most of these isotopes in many cases are the actinides. So then the idea is that we will collect all of these and then we'll have a continuous access to actinides, continuous meaning they are running the experiments and then we can select, we can harvest the actinides and we can access to all of these that are very difficult to access in other facilities like so. So we are, with the support of DOE, we were designing a beam line. I say we were because now it's being built. So where we will have all of these experiments, this kind of experiment that I show at EFRIB. So we started a couple of years ago. Now we complete the experiment this month. It looks in real life, something like this. And we are transporting this to EFRIB next month. So hopefully we will be ready for the start of EFRIB, that is this year actually. So in this year, this facility will be in operation. We'll have a new laser lab there and a new beam line where we can access to all of these actinides. So if you have ideas of rare actinide molecules, come to us. We'll be happy to provide at least the first spectroscopy. That's what we can do now. So there are many more molecules, many more actinides to study complementary aspects of nuclear physics or fundamental symmetries. I don't have time to speak about that, just to let you know that there is a lot more going on. So this is an exciting field, and not only diatomic molecules, also like chiral molecules here, nuclear spin independent parity violation scale with C to the 5. So this is exciting because we can build this very heavy nuclei and be very sensitive to this phenomenon. We are not the only ones playing in this field. So the group in Santa Barbara is doing something like Dima was suggesting. They trap radium ions and they inject gases to create the molecule already in a cold state, but it's unclear in which rotational numbers are going to create the molecule, right? How is the distribution of the population? So there is still work to go to do in this regard, but there is exciting progress. And there are ideas of assembling these molecules from cold atoms. So like David Emil and Timo Flake. So as I said, also applications beyond fundamental symmetries and nuclear science. So we are actually now combining efforts with some astronomers here at MIT and chemistries to study molecules for astrophysics. And this is something that we can do now with the technology that we have. So you need to know very well the rotational structure. So predictions, in their words, are not good enough to actually guide an astrophysical observation. So for some diatomic molecules, extrapolations are good enough, but when you go to polyatomic molecules, it's just very hard. So the idea is you do these experiments in the lab, and then you provide a guide to detect these molecules in space. And they came with a very long list of molecules. And for us, these are semi-stable molecules, right? Are many years. So that's something that in principle we can do with the technology that we have. So let me, with that end, summarize with this. So we have been working in improving both the sensitivity and the precision of the experiments. So the phenomena that we want to access is a product between nuclear and molecular parameters. So we are all the time working in finding the right nucleus, the right molecule, and improving the experiment to see a particular effect. So those provide quite complementary aspects of nuclear structure in our study of fundamental symmetries. So I showed you I should emphasize that was the first time that we did this kind of experiments in a short-lived molecule. So we had been learning a lot, and now we're at the point that we can measure the electrodefine structure. So we are working towards going beyond, because molecules, as I said, can enhance all of these parity and time reversal violations by many orders of magnitude. And radioactive molecules combine this nuclear and molecular amplification. Naturally, we can contribute to nuclear chemistry, quantum chemistry, right? We are creating these new forms of matter. So they are by itself very interesting. And I showed you just a quick example of why it's useful in astrophysics. And the most important is that this is just the beginning, right? So there is a lot more to do. There are many developments that still can be done. We are just starting with this work. Okay, and I would like to end and take all your questions.
Thank you very much for this very nice talk. Very challenging experiments and very beautiful results. I guess there are a lot of questions. Yeah, Dima.
Well, thanks so much. This is really amazing, amazing stuff. I have actually two quick comments and a question. So the first comment is that this idea of bringing molecular levels of opposite parity to near crossing and then working near that crossing, it's a kind of systematic thing available in molecules, but in atoms it is also possible. Of course, hydrogen is one case where you can do this, but there is also this amazing case in dysprosium. And in fact, Dave's molecular experiment is copied more or less from the dysprosium experiment, and we actually have still an ongoing experiment with that system at Mainz, and it's very similar. Otherwise, very, very similar. So that's the first comment. The second comment is there is, maybe you heard there is this proposal for the gamma factory at CERN, and that should also be able to produce all kinds of interesting isotopes in copious amounts. So maybe there is also possibilities for this work, this type of work that you are doing, and there are all kinds of interesting discussions. For instance, also for making even a specialized storage ring at CERN for radioactive isotopes. So I think maybe there could be more places to do this stuff. Yeah. And my question,
great.
Yeah, and my question, my question to you actually is this. So you mentioned this beautiful technique of collinear spectroscopy, and you mentioned that of course that decreases the lifetime, the time of interaction. I have a question for you. Has anybody thought of sort of once you have already this fast beam of making into a storage ring, and then you can reuse them, and then maybe you can get some factor back like this?
Yes, so there are tools to do that, right? So in fact, there was a lot of effort to have a storage ring at the solid, right? And a small one. I don't know if you know that.
Yes. That's exactly.
That's exactly one. Yeah, definitely. So that will be an advantage to do this kind of experiment when you reuse the molecules. Now, one we could think in a small one, right? So kind of a small scale side and low energy, but I don't see anyone developing that. Yeah. So we are still in the phase of. But now we did the spectroscopy.
It has been discussed, right? The molecular storage ring. I remember there was something about neutral molecules, I think, some years ago, but I don't know about charged molecules. Was that actually discussed in the literature?
Not that I know. So I haven't seen that. But yeah, that will be very interesting indeed. So for us, it will be good if we can trap, right? Because the technology has been developed. So groups like, as I say, Eric Cornell, we can already trap, but if we can avoid the trapping and sending it the storage frame, why not, right?
But see, this is basically, you can think of this, if it's possible, if then it's like in a sense a trap, combining the advantages of a trap and the collinear spectroscopy, right?
Yeah.
In a way. So maybe something to think about.
Yeah, thank you.
Are there further questions?
Not a question, but a comment. I mean, this was such a cool talk. You know, it's such a cool topic, and I'm very happy that you gave it. I'm very happy that you gave this interesting introduction, and I don't mind that people were getting bored, but I don't think anyone did. And yeah, congratulations also to the amazing rap video. This is probably, I mean, it raised the bar for the next quantum seminar series and everybody who is coming after this. And I think it's very hard to pull this off. That I mean, it can also be very, very quickly, very embarrassing. So, for example, if I would start now the same thing, for example, yeah. Anyway, thanks for this, and really interesting. That's the comment.
Yeah, thank you.
Yeah, Dima, do you?
Yeah, I have another question, if I may. So,
yeah, please.
Actually, Chris Dudman is also here. We have a project here, which is a collaboration of 3 groups: Ferdinand Schmidt-Kaller, Chris Dudman, and our group. It's called Tactica. It's on trapping thorium and in a crystal. So Wen Bing, who is working on that experiment, I think was here earlier. It's trapping thorium ions in a crystal of calcium ions. And in principle, with this apparatus, one can also study molecules with thorium. So what in your opinion is the most interesting system to study with this kind of an arrangement?
So there are some, because I don't know the kind of structure that the molecule, I was just trying to go here. So thorium molecules are indeed very interesting, right? So we have optical deformation in thorium-227, right? And I know thorium fluoride molecules are being studied or are being proposed in this regard.
By Victor Farbaum, yes. Mm-hmm.
So, and thorium oxide molecules, of course, but in the crystal, I imagine they will behave more like an ion-like, right? So I don't know what the structure you expect. I will imagine it will behave like a highly charged, or at least a 2+ or so. But yeah, definitely, thorium will be very interesting. So 229, 227 is where we think that there is optical deformation.
But in terms of the molecular species, you think that like thorium fluoride is an interesting
thorium fluoride plus, yeah, indeed.
Yeah, of course. Yeah. Thanks, Ronald.
So yeah, and good, and that's a main thing, because we need to. Let me show you here. So we need to slow down the molecule. So and that's not that easy to do that efficiently and trap and make it cold. And in ions, we have an idea of how to do that, right? So we can apply radio frequency fields and trap, but the neutral molecule is hard. We just don't know well, because the techniques that have been developed are buffer gas, right? We cannot use that effect efficiently for radioactive molecules, right? Because you're throwing away, you're kind of collimating the beam. One idea that was suggested is to create the negative molecular ion, and then trap the negative molecular ion, and then do the photo detachment. So that's a more gentleman process in which you produce the neutral already in a cold or relatively cold environment. And in the experiment, we are doing this exchange reaction, right? Radium fluoride neutral. But this seems possible. So to have the double charge exchange cell and produce radium fluoride minus, and then trap this. So that's one of the technologies that we'd like to explore. Yeah.
Okay, I have one question to you,
Yeah.
Ronald. I have seen that you are interested in lawrencium as well. This very heavy element. I think the isotopes, they are prolate deformed. Is it worth to go there?
Yeah, definitely. Super heavies are very cool, right? So this is your expertise, far from us. So it was mainly the theory that came, and I said, yeah, that's very cool, but it's not something that we can do. So somebody like you, but definitely, right? So the enhanced effective fields of these super heavies are, of course, they grow with C, and you have these high deformations. So they can be very large, more than 100 gigavolts per centimeter, 200 or 300, they are even quoting in these theoretical predictions. So that's something very interesting, definitely.
Are you planning to do the experiments in Tokai?
No, definitely no. So with this, it's already a challenge for us. Go with these molecules that we know we can produce in large quantities. I think our 4 is focusing with this new inline that we have at FRIB. So I was showing here, is focusing this actinides, all of this region that we will be able to produce. And the hope is that we will be having access to this almost full time, right? 24 hours, many days during the year. So that's the hope, if the harvesting program works as we think it will work.
Okay, thanks. Are there further questions or comments?
Yeah, I can maybe ask one just to this very slide shown here. So you show the actinides that you are interested in studying, you indicate where thorium is. And so that tells me that the uppermost ones are probably in the region of like plutonium or beyond. How are these produced at FRIB? Isn't this spallation of uranium that you will do? So how do you add those extra protons?
Yeah, no, so we will produce below uranium. So maybe it's slightly above, but yeah, so we will, I don't think that yields of plutonium will be particularly high. Yeah,
I see.
So we will be mainly interested in actinium, radium, protactinium, and thorium. Yeah.
Okay, thank you.
But yeah, thank you for the question and clarification.
Okay, thanks. Are there further questions? Yeah, it seems not to be the case. Then let's stop here. Thank you very much, Ronald, for this beautiful talk and accepting the invitation and being here together with us today. Thank you very much for all of the people joining us. I think we can close the session.
Yeah, but I just want to say, Ronald, when the COVID goes down, it would be really fantastic if you could actually come in person and hang out with us.
Yeah, definitely. Thank you, Dima. So I'm looking forward to that, right? Because we are kind of isolated from this community. I'm looking forward to get into your community, guys, and really learn from you and see these beautiful experiments. Yeah.
Thank you.
So definitely, Dima. So I'm looking forward to see you guys in person again.
Yeah, super. Okay, bye-bye.
Yeah, thank you for the invitation. Bye-bye.
Yeah,
bye, everybody. And send recommendations for next semester quantum seminar.
All right. Thanks.
Bye, everybody.
Bye-bye.
Bye-bye. Thanks for this talk. It was great.
Yeah.
Thank you. Yeah, thank you, Arnett. Thank you, Mustafa. So I hope that you guys, Mustafa, will record.
Yeah, thank you very much.
I just did a COVID test. I don't have it, at least according to the lateral flow.
I'm coughing most of the time, so I'm sorry about that.
Yeah, no problem.
Yeah, but it was a great, I think, occasion to meet you and also to discuss about the scientific result.
I mean, we have a conference series in August where I mean, it's not really that field, but it is mostly dark matter related. We have the Patros conference here in August. I don't know whether you are aware of that. It's the 7th iteration already. I just post here in the chat maybe the website.
Yeah, definitely. So I will be interested. So in principle, we can use these nuclear EDMs to constrain dark matter, right? Or we can.
Yeah. I mean, we're
There are
looking
many,
for the EDMs, oscillating EDMs, or fictitious magnetic fields, or energy shifts, and that kind of stuff. I mean, also the terbium experiment here is used for exclusion of dark matter, and that kind of, it all goes hand in hand in a way.
Yeah.
But it's not so. I mean, Patras is. I don't think that there were many, let's say, ion trappers or this quantum chemistry people in the recent years. But
yeah, I will look forward to that. Yeah, you send me.
I
links. Yeah.
Hey Ronald, just wanted to say hi.
Hi,
Thanks
Simon.
for the nice talk. Yeah, really awesome.
Yeah, thank you. Yeah, so nice to see you.
Yeah. Do you still get some time in the lab, or just teaching and researching?
Well, I love teaching and administration, but yeah, I hope to spend more time at the lab. Still, I go to the lab.
Yeah, I believe so. Yeah, cool.
Did you just say you love administration?
No. I would love to go to the lab. No.
Okay. Cool.
So by the way, Mustafa, for super heavy. So this is very interesting. So and what we have seen is that you can be very efficient with the molecule. So our efficiency, the total efficiency was like 1 in a few hundred. So that was very, very efficient, because if you choose the right molecule, although the structure is very complex, all these rotational levels overlap almost, right?
I see.
And then
I have to leave, but I assign Mustafa as a host, and then you can stay here until tomorrow if you want.
Just put me as a host.
Thanks again for the awesome talk, and goodbye. And see you in Mainz, hopefully.
Bye-bye.